Section 9.5 will conclude our Chapter 9, and this title is called Permutations and Combinations. What we're going to look at is we're going to look at different ways of counting things. Depending on what other math classes you've had before, you may have seen pieces of this like in college before. And pieces of this are going to harken back to some of the things we did in Elementary Math 1 as well. So to start with, I want to introduce a notation that I don't know if you've seen before. It's called a factorial. It looks like an exclamation point. It doesn't mean I'm super excited, though. Okay, that's not what it means. It actually has a formula associated with it. So when you see n with that little exclamation point, what it means is it means n times n minus 1 times n minus 2 all the way down until you get to the number 1. Let me skip the 0 for the moment and come down here and just do an example of one that's like that. So if I start out this example with a 4 and then that exclamation point, it means I just take the number 1 less than that, and 1 less than that one, and 1 less than that one until I get down to the number 1, and then I multiply those numbers together. So I take 4 times 3 times 2 times 1. And what do I get? What is it? 24. Good. So an exclamation point is a shorthand notation is what it is. It's kind of like exponents, right? I mean, if you have an exponent of 3, it means you multiply the number by itself 3 times. It's just a shortcut way of writing it. That's all one of these is, too. It's a shortcut way of writing something. Now, obviously, this only makes sense if I start with an n value that's bigger than 1, right? Because I can't go all the way down to 1 if I'm starting something smaller than that to begin with. Well, we do have, because it's a necessity, a definition for what 0 factorial would be, and 0 factorial is just the number 1. Okay, it's definition. I don't have to prove it or anything like that. It's just defined to be that way. Okay, so you see 0 factorial and you recognize that that's the number 1. All right, now I mentioned this a couple of times when we were looking at homework, fundamental principle of counting, and it is from Chapter 2 of your textbook. All right, so the fundamental principle of counting says the following. If you have an event m that can occur in little m numbers of ways, and capital event n can occur in n ways, then m followed by n can occur in m times n ways. And it sounds sort of funny, but it's a very straightforward idea, and here's a straightforward example of how it works. Pizza Planet. Yes, Pizza Planet. My son keeps telling me he wants to go to Pizza Planet. Offers 3 kinds of salads. 15 kinds, not kids, kinds. Kinds of pizza. And 4 desserts. How many different meals consist of 1 salad, 1 pizza, and 1 dessert? So this actually starts to feel a lot like the examples we were doing on the board. We are looking at 3 different things happening. Thing number 1 is we have to choose a kind of salad, and there are 3 choices we can make. Thing number 2 is we have to choose a kind of pizza, and there are 15 kinds of pizzas. So 15 choices we can make there. And then we get to choose a dessert, and there are 4 dessert choices we can make. And just like along our tree diagram branches, we multiply the results. That is a fundamental principle of counting. We multiply the ways different things can happen. So if I multiply 3 times 15 times 4, what do I get? What is it? I think 180 is what I have written down. 180 look okay? Is that okay? All right. 180 different options. I mean, you can imagine, like, this is how Sonic can tell you how many different drink combinations they have when they talk about adding flavors in something. And you could restrict it to adding in 1 flavor, or you could find out how many ways you could add in 2 flavors or 3 flavors or whatever. And of course, the spectrum keeps getting broader every time. But this would be a fundamental principle of counting example. There are 3 different types of counting, or 3 different types of ways we can count. The first kind is called a permutation of unlike objects. So what you're doing is you're selecting things that are not like one another. Okay? So, for example, when you had some of the drawing out of the hat kind of things you had, where all the letters were different, right? Those were unlike objects. When you drew out of the hat and there were coins and some of the coins were the same, those were like objects, right? Because some of them, there's more than one quarter, so some of the quarters are alike. Some of the coins are alike. So permutation of unlike objects looks like the following. Let me tell you first the notation. It's NPR. The N and the R sort of look like a subscript. They look sort of like they're very small and underneath where the P is. P looks like a capital P. The formula for this is N factorial. Remember we just talked about that notation a moment ago. Over N minus R factorial. The key for something to be a permutation is that the order in which it occurs matters. Okay, so if we wanted, here's an example I often give. If we wanted to have a race be run and we want to give awards to the top 3 people, you know, bronze, silver, and gold medals, the order matters. But if we want a race to be run and the top 3 people just extend their life in the event onto the next round, you know, they just go on to the next round like the Olympics when they're in different heats, then the order really doesn't matter. So you have to sort of weigh out, do I want to push hard enough to get first place in this round if it might cost me my time later on, those kinds of things. So permutation, the order matters. It's really important. Here's an example. Sometimes the phrasing will actually force it to matter, and sometimes the phrasing will leave it up to you to make the decision if the order matters or not. This is an example where it actually tells you. 50 people show up for a game show. 2 of the people will be selected at random to participate. How many different ways can this happen if the order matters? So if they tell you order matters, there's no excuse for choosing the wrong one, right? Because they told you. But if they don't tell you, you have to make a decision and think about, does it really make any difference? Would it make a difference to me if I came in first, second, or third? You know, those kinds of questions. On this one, the order matters, so it is a permutation. Now, the N right here is the number of elements. That is the number of people, things, places, whatever we're choosing from. So in this case, what is N? 50. There are 50 possible people that could be selected. The R is the number of people who actually are going to be selected, which would be 2 in this case. So this is 50p2. So you'll notice then that the N, the 50, is what's in the numerator with the factorial. And the denominator, it isn't R, it's N minus R. So in other words, I'll write it out this time, it's the 50 minus the 2. Now, there's a couple of things as I write this out that I want you to be aware of. Issue number 1, you really do not want to multiply out 50 times 49 times 48 times 47 all the way down to 1. There's 2 problems with that. Number 1, it's time consuming. Just practically speaking. Number 2, it's going to be a number your calculator can't handle. It's going to be too big. It's going to turn into scientific notation, which will then approximate things. So it's not especially helpful. Issue number 2 that you don't want to do is you don't want to think about this as being 50 over 48 and try to reduce the 50 and the 48 by dividing both by 2. That's not what we have here. We have 50 factorial and we have 48 factorial. So you can't reduce them in a traditional factoring sense. But what you can do is the following, and this is actually quite helpful, and it's faster than doing any of the other things you try anyway. I can write out the 50 times the 49 times the 48, and once I get a factorial that is identical to the one in the other location, I can stop. Because what that means is that means along the numerator right now, I have 48, 47, 46, 45, they all match. 48, 47, 46, they all match. So from 48 on down, all of those numbers are there on top and on bottom, which means that they can be reduced by canceling out at that point only. So what I really end up with at the end is I end up with 50 times 49, and that's all I end up with. Just those 2 numbers multiplied. And what do I get if I multiply those 2 numbers together? 2,450, that's right. So there are 2,450 different ways that those two people could be selected to participate in the game show if the order of the selection matters. And you might sort of imagine, like, why would it matter? Well, maybe the first person selected gets to go first in the game, and there's some sort of an advantage in doing that. Think Price is Right, if you're familiar with that. If you get selected at the first 4 people that are selected, you get to stay on whatever row they call that for a long time because you get to be there for every single possible, opportunity to get into the place, that kind of thing. All right, let's take another one. The next one is permutation, so still ordering matters, but these are like objects. Okay, so this is the example like Amanda was asking about where the coins were in the hat, and I had 5 quarters and 5 nickels and 5 dimes, and I had 10 pennies. Some of the objects are like other objects. Okay, they're indistinguishable. If I pull out quarter and it's the quarter number 1, in terms of value anyway, it's the exact same as quarter number 2 being pulled out. They're indistinguishable in their value to me. Okay, they may be distinguishable because they might actually look different, but in most cases we're talking about things that actually look a lot alike as well. So if we have n objects, we still have n factorial on top. There's no notation in front of this one like the NPR. It doesn't have that. But what we do is we divide by every different possible identical outcome in that hat. So imagine for me, back in that example that we did before, we had 25 coins, so we'd have 25 factorial on top. We had 5 quarters, so we'd have a 5 factorial on bottom. We had 5 dimes, so there'd be a 5 factorial on bottom. We had 5 nickels, so there'd be a 5 factorial on bottom. And we had 10 pennies, so there'd be a 10 factorial on bottom. So this can continue on for however many you actually have. Oops. I'll use an I there. It might continue on to have more than 4 options, right? What if I also had half dollars in there and dollar coins in there and, I don't know, some other crazy money in there. Now, I'm going to do an example that's not coins. I'm going to do the example with the word Tallahassee. What we're going to do is we're going to ask how many ways we could rearrange the word, the letters in the word Tallahassee to be a distinguishably different word. So as you can imagine, it doesn't really matter if I use the first S or the second S. It would look the same, right? So they're indistinguishable. Now, if I used this word and they were all different letters, then that would not be permutation of like objects. But there are some of these objects that are like other objects. Now, in particular, what I'd like to do is kind of what we did when we talked about our quarters, nickels, dimes, and pennies, is I figure out how many of each of these things I have. So how many T's do I have? 1. How many A's? 3. How many L's? 2. How many H's? 1. How many S's? 2. And E's? 2. So did I get all the letters? Okay, so these letters are very much like my different coins, okay? They're all in a hat and I'm pulling them out, so to speak. All right, so we are going to have a total. How many letters are there total? Not different letters, but actual letters. 11. So there are 11 letters if I count each individual letter in this word. There are 11 letters. So I've got 11 factorial on top, and then in the denominator I use each one of these numbers, 1, 3, 2, 1, 2, 2, with a factorial. Now I'm going to write it out, recognizing that it seems sort of silly to write 1 factorial out because it's just 1 and multiplying by 1 doesn't change anything. But if the numbers weren't 1s, we would need them all written in there, so I'm going to write them all in there. So 1 factorial, 3 factorial, 2 factorial, 1 factorial, 2 factorial, 2 factorial. Now 11 factorial is not very big. Your calculator can handle that. So if you want to multiply 11 down all the way out, that's fine. The other thing that you could do is you could write out the 11 until you get to 3. Because I do have a 3 factorial in the denominator that will cancel out really nicely with that. So you could stop there if you'd like. 1 factorials, of course, are just 1. So those numbers are really unhelpful. I don't really need them to be written again. What is 2 factorial? It's just 2 because it's 2 times 1. So I actually have 2 times 2 times 2. There are 3 2's down there. So when I'm canceling these out, the 3 factorials cancel, of course, because they're identically matching factorials. And then if you actually multiply this out, what do you notice the denominator is? 2 times 2 times 2. 8, which is in the numerator. Everything from the denominator will cancel with stuff from the numerator. You will always get a whole number out of these if you've done it properly. If you get a fraction, something went wrong. Okay? Because what you're doing is you're supposed to be counting numbers of ways that something can happen. You can't have something happen in a fractional number of ways. So what is 11 times 10 times 9 times 7 times 6 times 5 times 4? Say it for me again, Shelby.
831,600.
Is that what you guys have? A confirmation? Yes? Okay. Does that make sense? Is everybody good with that? Okay. Possibility number 3. Both the first 2 possibilities are called permutations, and in permutations, orders matter. Okay? In a combination order does not matter. Okay? So when you're combining things, this would be something where the order doesn't matter. So, the notation for this first is NCR. It starts out looking a lot like NPR. It has n factorial on top, and it has n minus r factorial on bottom, but it also has r factorial on bottom. That's the only difference, is that r factorial on bottom. Here, order does not matter. So this is the race that happens where it's just a qualifying round. People are just moving on to the next level. Another keen example that you see used is when somebody is creating some kind of a voting environment where the top 3 people get to be on a committee instead of the top 3 people having specific titles. Like if person number 1, you get the most votes, you're president. You get the second most votes, you're vice president, and third most votes, you're treasurer. Right? Then the order matters. It matters whether you got the most votes or not. If it's just the top 3 people are on some sort of committee and they're working together, then it doesn't matter if you got the top number of votes or the third number of votes, you're still going to be on the committee. Okay? So that's order doesn't matter. I use basically the same example. It just has a same situation where the order doesn't matter. 50 people show up for a game show. 2 of the people are selected at random. How many different ways can this happen if the order does not matter? Okay? And plenty of places where you would play a game that order wouldn't matter whether you were selected first or not. So this would be the 50C2. It would still be 50 factorial over 50 minus 2, which would be 48 factorial. But we have an additional piece in the denominator that's the 2 factorial. Now, we start working the problem very much the same way. I just write out 50 times 49 times 48 factorial, and I stop with the 48 factorial because it matches what's on the bottom. And then I have 2 or 2 times 1 down there as well. The 48 factorials flat out cancel. And if you want, you can multiply 50 times 49 and then actually legitimately divide it by 2. Or you could actually just recognize that the 2 divides something that's on top already. In particular, 2 divides 50 and then you get a 25. You don't have to do it that way, but if you recognize those pieces, you can do that. So you really just end up with 25 times 49, which is what? 1,225. You have half the number of choices that you had before because you divided it by 2 factorial, right? Okay. So we're going to do some examples with these different arguments. Some of these, they'll tell you where the order matters. Some of them, it's you deciding. Sometimes there's a decreasing number of ways something can happen. Sometimes you can repeat values. It just depends on the context of what you're working with. So for example, example 6, if all phone numbers on campus are 405-858, and then there's 4 digits after there, how many different phone numbers are possible? So this is a very standard example of of one of these cases. What would I have to do to find this out? Is it 9? Is it 10? Yeah, there's 10 options because you have the option of the number 0. So this is actually just a plain old fundamental principle of counting. Okay? We have 4 things I have to choose, and I have 10 choices that I can make in each category. So this is like my Pizza Planet example. 10 times 10 times 10 times 10. What's the result of that? 10,000. So there are 10,000 phone numbers on campus that we could have if we had this format for our phone numbers. Here's another example. There are 2 ways to do this problem, so I'll let you guys pick the first one, and then we'll see if you guys can think of the other one or not. A worship team practices 8 songs on Wednesday night for the Sunday service. If the minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? So is it a combination or is it a permutation? Does the order matter? It does. There's 2 reasons. Number 1, they kind of say it does at the end. And how many ways could the songs occur? Right? And how many different orderings could that happen? Now, from a very practical sense, it should matter. And you guys all have been in services where it's probably mattered and you've been like, that did not work well. Some songs do not flow into other songs. You do not do something peppy, upbeat during the, the offering or during the altar call. Or there's places where you do certain things and places where you just don't. It makes the service feel differently, right? So in that kind of a sense, too, it sort of makes sense. Just when they actually say it, they're asking us for the ways for it to occur. So it definitely does matter. So this is actually a permutation. Is it a permutation of like objects or unlike objects? They're unlike, right? they're 5 different songs that we're picking of the 8 or whatever it was, right? They're different songs. Okay, so they're unlike objects. All right, so this is a permutation. The permutation looks like this, NPR. And I'll show you again a different way to do this problem too in a minute. What is N? 8, because I have 8 that I'm choosing from. How many am I going to choose? 5. So this is 8P5. Excellent. So the permutation formula says that I'm going to have an 8 factorial on top, and I'm going to have an 8 minus 5 factorial on bottom. Okay, so this is 8 factorial over 3 factorial, which is 8, 7, 6, 5, 4, 3 factorial over 3 factorial. So if someone will grab a calculator for us and multiply 87654. 6,720. I think this one feels like a permutation problem, but it actually works also to do it as a fundamental principle of counting. You could think of this as I have 5 songs that I get to play. How many options do I have for song number 1? 8. How many options do I have for song number 2?
7.
And song number 3? Yep, and 5 and 4. And you'll see those are the same numbers we multiplied at the end. The only reason this works here is because number 1, order matters. If the order didn't matter, I couldn't even do it like this. And number 2, we're assuming that we're actually choosing 5 distinctly different songs because of the way that the question is worded. How many ways can I select 5 songs? And again, we're assuming we're not picking the same song multiple times. Okay?
So if we had a problem like that on our test, could we use the fundamental principle?
Yeah, you can choose either one of them. Yep. All right, the next thing we're going to do is we're going to look at a deck, of cards, a standard deck of cards. So a standard deck of 52 cards, we're going to look first at how many different 5-card hands you could be dealt. So think with me now, again, permutation, combination. Does the order matter when you're dealt a hand of cards?
Well, depends.
So why would it depend, Rachel?
Maybe it doesn't.
Maybe it doesn't. A couple of you were saying it doesn't matter. Why do you think it doesn't matter?
Because you could like shuffle them or whatever. It doesn't matter what order they're in.
Shuffle them in your hand, is that what you mean, Lacey? Yeah, and in fact, that's usually what you do. The first thing that happens, no matter what card game you're playing, is you take the cards that somebody gives you and you put them in some kind of an order that makes sense based on the game you're playing, right? Maybe it has to do with the suit that they're in, maybe it has to do with the number order of what's going on. And it doesn't just work for standard 52 card deck. This works for Skippo and, Phase 10 and there's a whole bunch of games. But, any kind of game that you're working with cards in, the first thing you use, Old Maid, right? You move things around. And you move them around for whatever reason. So since the order doesn't matter, is it a combination or a permutation? Combination. So anything that you're doing with a deck of cards is a combination problem, all right? So what we're wanting to know on the first question is how many different 5-card hands can I have? So how many cards are there to choose from? 52. And how many am I choosing? 5. So this is 52C5. All right. So in the numerator, what will I have? 52 factorial. In the denominator, I will have 52 minus 5 factorial and 5 factorial. Yeah. What's 52 minus 5? And you'll notice that in a combination, whenever you get to this point, the two numbers that are in the denominator add to 52. Do you guys see that? 47 and 5, they add to 52. That has to work. So just like on the other examples, I don't really want to multiply a bunch of these numbers out. But what I would like to do is to write them out until I can get one to match. Now, as it is, I've got the 5 factorial still down there, and there's not going to be a 5 factorial in the numerator, so I'm going to write it all the way out as well. All right, so the first big problem is the 47 factorial, and those go away. The next thing I'd like to do is you can do one of two things. You can either just multiply everything on top, multiply everything on bottom, and divide, and that's perfectly fine. You can do that. Or you can reduce things. So I kind of like to reduce things. That's what I'm going to show you. The 5 and the 50, that divides to 10. And sometimes you have more than one choice on the division here. 4 and 48. Well, 48 divided by 4 is actually 12. Right? 3 and 2 multiply to give me 6, right? 3 times 2 is 6. Well, I could take the 12 that I just had a minute ago and divide it by 6 to give me 2. There might be some other combination of things that you're multiplying and dividing out differently. That's fine. You'll still end up with the same answer at the end. The values I have are 52, 51, 10, 49, and 2. You might have different numbers, but you'll have the same answer at the end if we both did them correctly. How many different 5-card hands do we have? What'd you have, Rachel?
I got 2,598,960.
That's correct. Does that look right? That's a lot of hands of cards, isn't it? And that's just because the order doesn't matter. What if the order mattered? It'd be even higher, right? A lot higher, in fact. All right, so there's 2,600,000 roughly different hands of cards from a 52-card deck. Question B, then, wants to know how many different 5-card hands are there that are all diamonds? Do you know what that's called when people play poker, if you just get all of one suit? I think it's called a flush, isn't it? Isn't that what they call it? I think that's right. So all of one suit is generally uncommon. It doesn't happen very often. And so we would like to know how often it does in fact happen. So how many hands of cards would contain all diamonds? Well, how many diamonds are there? 13 diamonds. There's 13 of every suit. How many of those 13 am I picking? 5. So again, the order doesn't matter. So this is 13C5. So my numerator is 13. My denominator is 13 minus 5 factorial, 5 factorial. So what is 13 minus 5? It's what? 8. Yes. So 8 is the larger number, so we will write 13 down to 8. The 8 factorials, they match. And then I have 5, 4, 3, 2, 1. So there went the 8 factorials. You can actually pair these up really nicely. Notice if I take 5 and 2 combined, what is 5 times 2? 10, and I have a 10 in the numerator. And what's 4 times 3? 12, and I have a 12 in the numerator. So that one actually pairs up really friendly. So this result ends up being 13 times 11 times 9. So what is 13 times 11 times 9? I mean, there's still 1,000 hands plus, a little bit more, that are all diamonds. But that's not very many compared to the 2 million I had before, right? And that's what part C is. Part C is what is the probability then of getting a 5-card hand of all diamonds. Well, how do we find probability?
Over all possible outcomes.
The number of hands of all the diamonds, that was part B, divided by the number of any combination. Anything could happen, and that was part A. So this is the 1287 on top, and on bottom is your 2,598,960. So go ahead and divide those. Tell me what you get. It's a very small number.
0, 0, 0, 5, pretty much.
I think that's a fair value. 0.005. If we turn that into a percent, this would be a 0.05% chance. Like, it's never going to happen, right? I mean, like, that's pretty well not going to happen. Not often, anyway, yeah? Okay, we're going to do the next one, and it's going to be a little bit different. So no more hands of cards, but you could do this with anything in the hands of cards. We could talk about getting aces and something else, so a hand that has 4 aces in it or something like that, the same way. We're going to get a committee. Do you remember what I told you about committees a little bit earlier? Does order matter for committees? No, it doesn't. So keep that in mind. We have a committee of 3 people, and it is selected at random from 7 seniors, 5 juniors, and 3 sophomores. We want to know the probability the committee consists of all seniors. So what we're going to do is we're basically taking like this same model that we did back on example 8, but we're starting with question C. They just say from the get-go, what's the probability of this happening? Well, in order to find the probability, we have to kind of backtrack and do parts A and B. We have to find that numerator, we have to find that denominator. So in other words, if we want the probability of all juniors, just like we wrote out on the last example, we want the number of ways of getting all juniors.
All seniors.
Oh, did it say seniors? I'm sorry. Okay, the number of ways of getting all seniors. compared to the number of ways of getting any committee, right? Any collection of people. So I'm going to do this in 2 steps. I'm going to find what's the value of the numerator. I'm going to find what's the value of the denominator, and then I'm going to divide them. So what's the way of getting, or how do I get all seniors? Not the probability of it, but just the number of ways. Well, how many seniors are there? 7. 7C what? Not 15. I want a committee of all seniors. There you go, 3. I want a committee, right? The committee consists of 3 people. So from the 7 seniors that are around, that exist, that are prepared to take on this responsibility or whatever, I want to pick 3 of those people. That's my goal, in other words, in this problem, is I want all seniors to be picked. All right, so combination means to take 7 factorial on top, 7 minus 3 factorial on bottom, and then 3 factorial on bottom. So what is 7 minus 3 factorial? 4 factorial over 3 factorial. So 7, 6, 5, and 4 factorial over the 4 factorial, and then 3, 2, and 1. So the 4 factorials cancel. What happens with the 3 and the 2? Yeah, they cancel with that 6. So how many different ways are there of getting all seniors? 35. And I'm going to need that in a minute. So I'm going to box that in to remind myself. The next thing I want to do is the number of ways of getting any committee. All right, well, how many people are there that are applying to be on these committees?
15.
Yeah, that's your 15, right, Shelby? The 15 people. But I have a committee of only 3 people, so I'm still only picking 3 of them. I'm just picking 3 from amongst everybody now. So my numerator is 15 factorial. My denominator is 15 minus 3 factorial. And then the denominator also has a 3 factorial in it. So this is 15 factorial over 12 factorial, 3 factorial, or 15 times 14 times 13 times, there's my 12 factorial, over the 12 factorial, and then 3, 2, and 1. So the 12 factorials, of course, cancel. What does the 3 reduce with? 15 to give me 5. What does the 2 reduce with? 14 to give me 7. So I actually have 7 times 5 times 13, which is what? 455, right. So there are 455 total different committees that I can have. So now I can find the probability of all seniors by doing what? 35 divided by 455. And if you divide that out, I'll just give you what this one actually is. It's 0.0969. So this is roughly a 10% chance. 7, I'm sorry. Yes, it is a 7. My paper is a little too far away. 0.769. So this is roughly an 8% chance, right? It's not very likely still, but definitely more likely than my hand of all diamonds. All right, one slight variation and then we'll be done for today. The probability that has no seniors. So what would I do to get the probability that I have no seniors? Well, I take the number of ways that I get no seniors compared to the number of ways of getting any committee. Well, I've already calculated that value, right? I don't need to calculate that denominator again. It's 455. It's going to be 455 if I do it again. And how do I calculate the number of ways of getting no seniors? Yeah, just do juniors and sophomores. So how many juniors and sophomores are there? 8. And I'm selecting 3. This is 8 factorial over 8 minus 3, which is 5 factorial, 3 factorial. 8, 7, 6, and 5 factorial over 3, 2, 1. There's those 5 factorials. What happens with the 3 and the 2? Takes out the 6. What is 8 times 7? 56. And I already know the denominator because I already did it. So the probability of getting no seniors is 56 over the 455 from our last part of the problem. And if I divide this one out, I get 0.1231. Slightly higher, right? Because I started out with 8 choices instead of 7, right? That's the reason. All right.